Waveform patterns reveal what a machine is doing between the peaks shown in a spectrum. A spectrum tells us which frequencies are present. A waveform shows how vibration unfolds through time. That difference is essential when investigating mechanical looseness. Two machines may display similar harmonic families yet produce very different time waveforms. One may generate a clean impact once per revolution. Another may produce irregular bursts. The spectrum suggests a possibility. The waveform helps us understand the mechanism. This presentation examines rotating looseness and classic looseness. Terminology and detailed examples should be checked against the authorized Mobius Institute Category 2 manual. The objective is practical. Recognize each visual character, understand why it appears, and verify the mechanism. Begin with a rotating shaft supported by bearings. Under normal conditions, these components move as a connected system. Clearances remain controlled, and contact occurs where it should. Looseness changes that relationship by creating an unintended degree of freedom. A loose fit, bearing, hold down, keyway, coupling, or support can permit movement. The component may move normally, then strike or release energy when clearance is taken up. In a waveform, an impact appears as a rapid change in amplitude over a short time. The event may be large or small, regular or irregular, isolated or repeated. Waveform analysis is useful because it preserves timing. The horizontal axis is time. The vertical axis is vibration amplitude. Amplitude may be acceleration, velocity, or displacement. Acceleration is often sensitive to short-duration impacts. Velocity supports overall vibration evaluation. Displacement can help describe lower-frequency shaft motion. Before interpreting a pattern, verify unit, sensor location, frequency range, sampling rate, and time span. The first question is not, does this look like looseness? The first question is, what exactly am I looking at? Check horizontal, vertical, and axial directions. Record operating speed and load. A waveform without operating context is evidence, but incomplete evidence. Now consider a rotating component with clearance on a shaft. During each revolution, force changes the component's position. At a particular angular position, the loose part contacts a surface. If speed and geometry are stable, the impact may occur once per revolution. At 30 revolutions per second, the repetition interval is approximately 1/30th of a second. The impact is brief, while the interval between impacts is longer and quieter. This is the basic character associated with rotating looseness. A real machine may strike more than once per revolution. A damaged keyway, loose bearing, or coupling may create several contact events. Look for repeatability over several revolutions. Do larger impacts occur at approximately the same interval? Do the events align with 1 times running speed or with multiple events per revolution? A clean rotating looseness waveform concentrates energy into sharp, high-slope events. The events repeat in relation to shaft rotation. The waveform between impacts may be quiet or contain decaying structural ringing. The impact excites natural frequencies after physical contact has ended. Do not confuse ringing frequency with the repetition rate. The event rate describes how often impacts occur. Ringing describes how the machine responds. Repeated impacts can produce running speed harmonics in the spectrum. A smooth sine wave is dominated by one frequency. Sharp edges require many harmonics. Harmonics alone do not prove looseness. Misalignment, rubbing, distortion, and damaged couplings can also generate harmonics. Crest factor and kurtosis may support the interpretation, but neither is a diagnosis. A loose component can also create amplitude modulation around a resonance. In the spectrum, the resonance may be surrounded by sidebands spaced at running speed. Now consider classic looseness at a stationary structural interface. Examples include a loose foundation bolt, deteriorated sole plate, cracked pedestal, or loose housing. The shaft may rotate normally while the housing or base moves abnormally. Classic looseness can produce repeated impacts, but the pattern may be irregular or load-dependent. The waveform may show multiple impacts, asymmetrical excursions, or clipped-looking regions. A support may lift, release, and return to contact as forces change. This behavior reflects nonlinear contact rather than one continuous linear spring. Nonlinear behavior produces distortion, and distortion produces harmonics. Classic looseness is often associated with many running speed harmonics. Compare waveforms at the housing, base, and support in several directions. A strong impulsive response concentrated at the support makes structural looseness more plausible. A dominant vertical response may indicate liftoff or settlement, but it remains a clue. Phase measurements can reveal unexpected relative movement between locations that should move together. Operational deflection testing, impact testing, and physical inspection can resolve uncertainty. Rotating looseness is tied primarily to the rotating assembly. Classic looseness is tied primarily to a stationary support or structural interface. Both conditions involve impact and nonlinearity, so one waveform may not be enough. Ask, what part of the machine must move to create this pattern? If the source rotates with the shaft, investigate rotating fits, keys, couplings, or bearing clearance. If the source is stationary, investigate the housing, foot, foundation, pedestal, or frame. Ask when the movement occurs, at a consistent angle, changing load, or changing speed. Begin every investigation with safety and authorized machinery access procedures. Review historical vibration, spectra, waveforms, process conditions, speed, and recent maintenance. Confirm sensor mounting, cable condition, range, overload status, sampling rate, and bandwidth. Collect a waveform long enough to show several shaft revolutions. When speed changes, use a tachometer, phase reference, or order tracking. Compare waveform, spectrum, phase, directions, and measurement locations. Do not overlook multiple faults occurring at the same time. A machine may combine unbalance with loose support or misalignment with a loose coupling. In one representative case, a sharp pulse repeats once per revolution with decaying ringing. This combination is consistent with a rotating impact source. In a second case, uneven impacts are strongest vertically and change with process load. This raises suspicion of structural or support looseness. In a third case, changing speed makes the waveform appear irregular in fixed time. Order tracking may show that the impacts remain synchronized with rotation. In a fourth case, high-frequency bursts may indicate a bearing problem rather than looseness. Envelope analysis, calculations, phase, and inspection are needed before deciding. A common mistake is to call every impulsive waveform looseness. Impacts can result from bearings, gears, rubbing, cavitation, lubrication, electrical events, or measurement artifacts. Another mistake is treating high crest factor as proof of a severe fault. A third mistake is assuming that many harmonics have one unique diagnosis. A fourth mistake is ignoring load condition. A fifth mistake is relying on a single measurement point. A clean animation can connect physical movement, waveform, and spectrum. A second animation can show a machine foot lifting and returning to contact. Keep graphics simple. Their purpose is to connect physical movement with measured behavior. Use representative examples unless a documented case history supports the data. Now build a practical decision framework. If impacts are present, ask whether they are repeatable. If repeatable, compare the interval with running speed and known fault frequencies. If tied to rotation, determine whether the source rotates with the shaft or remains stationary. If the pattern changes with load or direction, investigate nonlinear contact and structural movement. If ringing is present, identify the resonance separately from the impact rate. If evidence points to looseness, inspect the relevant interfaces before recommending corrective action. Corrective action may restore a fit, repair a foundation, replace fasteners, or address alignment and loading. Tightening a bolt without understanding why it loosened may provide only temporary improvement. After repair, repeat the measurement under comparable conditions. Confirm that impacts and harmonic content have reduced as expected. The strongest analysis combines waveform, spectral, spatial, operational, and physical evidence. Waveform evidence shows what happens in time. Impacts, bursts, clipping, asymmetry, and ringing. Spectral evidence shows frequencies, harmonics, sidebands, and resonances. Spatial evidence shows where vibration is strongest and how it changes across directions. Operational and physical evidence show how the condition responds and what inspection reveals. Waveform analysis is not picture matching. It connects time, force, motion, and structure. A sharp pulse is a moment of change. A repeating pulse is a relationship. Ringing is a response. Harmonics are a consequence of waveform shape. Location is a clue to mechanism. An operating condition reveals how the fault behaves. Capture a reliable waveform. Confirm the time scale, compare locations, and inspect safely. The goal is not simply to recognize a waveform. It is to make a sound maintenance decision. For study, compare this presentation with the authorized Mobius Institute Category 2 manual and site procedures. A confident analyst explains what the data shows, what it does not show, and what will resolve uncertainty. That is the practical value of waveform patterns. When looseness develops, the waveform can support early action and intelligent investigation.